Hi, everybody, and welcome to today's session of the Spectral Geometry in the Cloud seminar. Today we have Luigi Provenzano from Rome, who will talk to us about the critical points of Steklov eigenfunctions. Luigi, the floor is yours.
Okay, thank you very much, Jean, to you and to all the organizers for this opportunity. It's always a great pleasure to give a talk here in the seminar in the clouds. So today I will talk, as you said, about I will give you some information on the critical points of Steklov eigenfunctions, and this is a joint work with Luca Battaglia from Roma Tre and Angela Pistoia, who is a colleague from Sapienza. So the first two slides, maybe you have seen them very often in this seminar, but let me just show them. So the Steklov problem and the Dirichlet-Neumann map, which are the the operator that I will be considering today. So M will be a compact connected Riemannian manifold of dimension n greater or equal than 2 with a smooth boundary. Everything will be smooth for me today. And the Steklov problem on M is finding a function u in M and a number sigma, such that u is harmonic in M and the normal derivative of u is equal sigma u on the boundary. Nu is the outer unit normal. And as is well known, we have an increasing sequence of non-negative eigenvalues of finite multiplicity diverging to plus infinity. As concerning eigenfunction, we can choose them to form an L2 basis, an orthonormal basis of L2 of the boundary, of course. This is the standard choice. And if you choose the eigenfunction in such a way, the eigenfunctions in the interior form an orthogonal basis of the harmonic functions in H1. So this is a fact. And this is the Steklov problem and the Steklov eigenvalues. So, however, the Steklov eigenvalues sigma k are the eigenvalues of the Dirichlet-Neumann map also, can be interpreted as the eigenvalues of the Dirichlet-Neumann map, which is a map acting on functions on the boundary. Namely, it maps a function on the boundary to the normal derivative of its harmonic extension inside the manifold, inside M. So the eigenvalues are the same. And if we look at the eigenfunctions of the Dirichlet-Neumann map, those are exactly the traces, or if you wish, since we are in a smooth case, the restriction of Steklov eigenfunctions on the boundary. So you see already here the notation that I will use through all the talk. With U, I will denote functions in the interior, saying in M, in the manifold, and with phi, the restriction or the traces on the boundary, so functions on the boundary. I will use these two letters to denote objects. Just to complete this brief introduction on the Steklov problem, the first eigenvalue, which I will call sigma 1, I prefer to start with 1, it's 0, and the first eigenfunction is constant. And every eigenvalue can be characterized as usual through the min-max principle with for the associated Rayleigh quotient. Okay, that's something very standard, very custom. You have seen this a lot of time before here. So let me go on the topic of my talk. And what I will tell you today is something about formulas, establishing formulas which relates the critical points of UK, Steklov eigenfunction, phi k, Dirichlet-Neumann eigenfunctions, and the topology of M, and eventually of the boundary and boundary nodal domains. We will see that. So, but let me start with some, review some history of this kind of results. So the study of the critical points of solutions to elliptic PDEs is a vast topic. Actually, I'm not really an expert. I started looking at these things since very recent, thanks to some colleagues in Rome. And in the Steklov case, a fundamental reference is a paper by Alessandrini and Magnanini, who was pointed to me by Josip Porterovich some time ago, if I remember well. So just to give you a flavor of kind of results of that we will discuss, let me just state the result of this 1994 paper. So just for this result, I will slightly change the notation for the eigenvalues just for these two slides. So I will denote by sigma k with the parentheses the Steklov eigenvalues, but I do not repeat them according to the multiplicity. So these are just the values attained by the eigenvalues. And I will call by mu k the multiplicity of each of these eigenvalues, namely the dimension of Vk, the corresponding eigenspace. And let me introduce then other three quantities. Okay, the first is k with k. Okay, is not really happy notation, which is the maximal number of critical points of an eigenfunction in the eigenspace Vk. Capital delta K, the maximal number of interior nodal domains of an eigenfunctions in Vk, and small delta K, the maximal number of boundary nodal domains of an eigenfunction in the kth eigenspace. And so the kind of results in this paper are those inequalities relating these four quantities. And this has been established in this paper for simply connected planar domains. They can be easily stated for simply connected surfaces, let's say. And so these are inequalities between these quantities. Namely, the number of boundary nodal domains can be bounded in terms of the interior nodal domains, the number of interior nodal domains in terms of multiplicity, the number of critical points in terms of the number of interior nodal domains, multiplicities in terms of the number of critical points. So you see that these four quantities, nodal counts, number of critical points, multiplicities, are somehow related, at least in this simply connected case. In particular, now I come back to my notation that I will use again from now on, that the true case plus one eigenvalue, case plus one with when I repeat the multiplicity, is at most 2k. So we have these results imply a multiplicity bound on the case plus one eigenvalue. And again, I repeat, we can see relations between these four quantities from these inequalities. And so there have been studies on bounds for certain of these quantities. In particular, the study of multiplicity bounds for general surfaces has been an object of various research, for example, Karpukhin, Kokarev, Polterovich, and Jam, of course. This for what concern multiplicity bounds. Concerning nodal counts, we have, for Steklov eigenvalues in the interior, we have the paper of Cutler and Sigillito, which deals also in the two-dimensional case with the counts of boundary nodal domains, and the paper by Hassanejad and Sher of 2022. Again, especially for nodal counts of Steklov eigenfunction. So interior nodal domains, much is known, while the problem is more delicate in higher dimension and greater or equal than 3 for the Dirichlet-Neumann eigenfunction, namely for the boundary nodal domains. I will get back to this at the very end of the talk, actually. Okay, so for people interested in, having some information on the study, on the critical points of solutions to elliptic PDE, a nice survey is the one of Magnanini again, and specifically there is another paper which concern particular harmonic functions in the plane, again by Alessandrini and Magnanini of 1992. Maybe I will cite it also later. So that's more or less about the some reference, some really essential references on this problem. And now I'm going to enter into the core of the matter, and let me just cite the fundamental tool, say classical tool that we will employ, which is the Poincaré theorem. So I will employ this in the following. Well, I have an n-dimensional manifold. Riemannian is not, metric does not play any role actually here. And let V be a smooth vector field on it with only isolated zeros. Moreover, if the manifold has a boundary, we assume that the vector field is outward pointing on the boundary. And then we have the sum of the indexes of the zeros of the field does not depend on the vector field, depend only on the topology of the manifold, and it is actually equal to the Euler characteristic of M. This is a classical result. I just put here this slide to recall very rapidly what is the index of a vector field at an isolated zero. You can think first in the case at the case of vector fields on Rn on the Euclidean space. You have an isolated zero. You take a small sphere around this isolated zero. On this sphere, the vector field does not vanish. So you normalize it on the sphere and use it to define a map to the sphere and -1 sphere to itself. And so the index is the degree of this map. here in the two-dimensional case, around any of these zeros, you put a circle, and then you normalize the vector field on this circle, and then this defines a map from the circle to itself, and then the index is the winding number of this map, just that. So here we have vector fields with indexes -1, 0, 1, 2, etc. This is a picture from the Milner book. This is just to recall what the index is. I don't want to enter into more detail. So essentially, the Poincaré theorem relates the index of zeros of vector fields to the topology of the manifold. And so let me state the basic formula established in that we will be later employed to study critical points of Steklov eigenfunction. And this basic result is stated as follows. And only for this, I will sketch just a brief proof. So I have a smooth compact Riemannian manifold connected, if you wish, with smooth boundary. And let U be a smooth harmonic function in M. The Q an harmonic function, and phi, as you see, is its restriction on the boundary. So I call phi its restriction on the boundary. And I make these three assumptions in order to state the result. I assume that U has isolated critical points inside the manifold. I assume that phi as a function on the boundary has only isolated critical points on the boundary. And I also assume that the gradient of U does not vanish on the boundary. And then we can conclude that the sum of the indexes of the critical points of U, so the interior critical points of the harmonic function U, is equal to the Euler characteristic of the manifold minus the sum of the indexes of the boundary critical points, so now as the critical points of a function on the boundary, but just those where the normal derivative of U here is it positive. Okay, so this is a formula with this equality. So we have this identity, this formula that relates the indexes of the two functions, U on the interior, phi on the boundary, and the Euler characteristic and the topology of the manifold. And again, this statement is reminiscent if you translate it a bit to some inequalities. Actually, they have inequalities that have been stated for harmonic function in the paper of 1992. Okay, only for this I will sketch the proof. It's really an idea of the proof. I will not, of course, enter into the details. In fact, I used pictures just to represent the situation. These are just pictures. Please take them as they are. So we have a general harmonic function, so its gradient does not need to be outward pointing on the boundary, so we cannot use Poincaré theorem directly here to the gradient of this harmonic function. So a natural idea is to consider the double of this manifold. Since we have a smooth manifold, we have a tubular neighborhood, a well-defined tubular neighborhood of the boundary, and use this tubular neighborhood, this scalar neighborhood, to glue together two copies of M. You can imagine that around the gluing, this manifold is a product, essentially, okay, of the boundary times an interval. Okay, now that we have produced this double, is a standard construction, we have to extend the function U in this double manifold, of course, to a function U tilde. Of course, if you just extend by taking U also in the other copy of M, you obtain a continuous function, which is, of course, not differentiable at the gluing, clearly. Then we have to smooth it out in a suitable way in a small tubular neighborhood of the gluing, of the boundary, which is now an hypersurface. But we want to do so in such a way that the values of the function exactly on the boundary, let's say on this hypersurface now, is preserved. So we want that U on partial M on this gluing hypersurface does not change. And we can do in an explicit way. So this, again, is a picture that represents what we are doing with this smoothing. We're smoothing this function. So we have produced a new function, U tilde, starting from U, which has the same values of U, that is phi, on the gluing. And now we want to look at the critical points of these functions. Of course, the first thing to control is that we have to take this tubular neighborhood where we perturb our function U such that gradient of U has no zeros. yes, you can take. Of course, you have to answer to Alexandra. Of course, you have to take a suitable metric if you wish, a product metric where you were in a tubular neighborhood of the boundary, let's say, when you glue. But this does not affect the critical points or their index, let's say, their behavior. Yes. Anyway, it's not needed that it is Riemannian. Okay. For our consideration. Oh, okay. So we want that in this, okay, let me go back. In this thin strip, the gradient of U has not zeros. We can do it because by hypothesis, a gradient of U has no zero on the boundary. So by continuity compactness, it has no zero in a neighborhood of the boundary. So what are the critical points of these new functions? These are, of course, the critical point of U in M, counted twice. These are in the part outside this polar, this tubular neighborhood, and are the critical points of this U tilde inside the tube, the collar. So we have to identify these new created critical points. So where are those new critical points in the thin tube? Okay, again, please take this picture as it is. I didn't know how to produce a picture to explain things in a more clear way. They are just the points on the boundary, that is now where we glue the two manifold, where phi, the restriction, has a critical point. So they exactly correspond to the critical points of phi on the boundary, because in normal direction, the derivative, when we have smoothed out the function, is zero. So we need also in the tangential direction, it is zero. And if we do things properly in this tube, in this tubular and collar neighborhood, there are no other critical points. So in these tubular neighborhoods, the only critical points are those coming from phi, from the critical points of phi, of the restriction on the boundary, just that. So we have identified all the critical points of tilde U. And by assumptions, these are isolated. So we can apply Poincaré-Hopf theorem and deduce that the Euler characteristic of the double is, of course, twice the sum of the indexes of the critical points of U, so the one in the part where it is okay, plus the indexes of the critical points of U tilde in the tubular neighborhood, in the collar, let's say. So we need to compute the index. In particular, we need to see how this index is related to the index of the gradient of phi as a function on the boundary. But this is not hard to do. And this depends only on the sign of the normal derivative of U at those critical points of phi. And it turns out that this index, the sum of the index of U tilde, of the gradient of U tilde at a critical point, is exactly equal to the index of the tangential gradient of phi in the critical points where the outer derivative, normal derivative, is positive, and is minus its index where the outer normal derivative is negative. This is quite easy to do because in the normal direction, the function U tilde is degenerate and the second normal derivative has the sign exactly as the sign of normal derivative of U. Okay, I don't enter into this detail, but just look at the last line. If you instead of having minus, you have plus, then that is just the Euler characteristic of the boundary because you apply again Poincaré-Hopf theorem. So you use that, and you use also the fact that the Euler characteristic of the double is twice the Euler characteristic of M minus the Euler characteristic of the boundary. You sum up everything and you conclude, and you have the identity of the theorem. So I've been a bit, say, fast on this proof. I didn't want really to enter into the details, but these are the main ideas behind that, quite standard. Okay, so that was the only proof actually that I will show you today. I will now discuss about corollaries and other consideration on this. So let me just do some remarks. So we assume that U and phi had isolated critical points, but if they are more, in particular, if they are Morse function, the index, that index that we have here, can be replaced by -1 to the power the Morse index of the function, which is the number of negative eigenvalues of the Hessian, if you wish. Moreover, if these functions are Morse and the dimension is 2, we know that all interior critical points must be saddles, so index -1. And all boundary critical points must be maxima, so index -1, or minima, index +1. And so we deduce this more explicit formula, which counts the number of interior critical points, so critical points of U, which is equal to the number of maxima of phi on the boundary, but just where the normal derivative is positive, minus the number of minima where the normal derivative is positive, minus the Euler characteristic. Then we will see later how render this formula even more explicit, even more connected to the geometry of the surface. Okay, now what we want to do is to apply this, say, basic theorem to Steklov eigenfunctions. So I recall again the hypothesis of the theorem on the harmonic function U and on its trace phi. And these hypotheses are that U must have isolated critical points in M, that phi has isolated critical points on the boundary, the gradient of U does not vanish on the boundary. Of course, we cannot expect that this always holds at non-constant Steklov eigenfunction, of course, because we can have many examples where these are not true. I will show you also later, but you all already understand what they are, the disks, the eigenfunction disks, of course. But it is reasonable to expect that they hold generically, means that there is a dense subset of smooth matrix for which these properties hold. And now a recent paper by Wang, 2022, it proves, the author proves that these three properties that I list here are generic for Steklov, for non-constant Steklov eigenfunctions. Namely, the eigenspaces have dimension 1, which means that Steklov eigenvalues, are generically simple, that non-constant Dirichlet-Neumann eigenfunction are Morse on the boundary, and the 0 is a regular value of a Dirichlet-Neumann eigenfunction on the boundary, which means that if we have a 0 on the boundary of a Dirichlet-Neumann eigenfunction, the gradient, tangential gradient, there does not vanish. Not that 2 and 3, and if you wish 1, 2, and 3, these are statements about Dirichlet-Neumann eigenfunctions. Means the restriction of the Steklov eigenfunctions on the boundary. So we are speaking about the boundary, the problem on the boundary, the Dirichlet-Neumann problem. Okay. If you look at hypothesis 2 and 3 of Wang, these imply our hypothesis 2 and 3, calligraphic 2 and 3. In particular, if non-constant Dirichlet-Neumann eigenfunction are Morse on the boundary, means that on the boundary, our eigenfunctions have generically isolated critical points. Morse imply isolated critical points. 3, 0 is a regular value of Dirichlet-Neumann eigenfunctions. Combined with the Steklov boundary conditions, gives that you cannot have generically the gradient of a Steklov eigenfunction is 0 at the boundary. The point is that our hypothesis 1 does not follow from these generic properties of Wang, because we know that we need that U has isolated critical points inside them as a Steklov eigenfunction, not just Dirichlet-Neumann eigenfunction, let's say. So we managed to prove, just to complete, let's say, the statement of Wang, some generic properties of Steklov eigenfunction, so eigenfunctions in the interior. And so 4 and 5, we have added 4 and 5 to generic properties enjoyed by Steklov eigenfunction. And these properties are that non-constant Steklov eigenfunction are Morse in M. So this is a statement on Steklov eigenfunction in the interior. And also that the 0 is a regular value of a Steklov eigenfunction in M. Well, just point 4 is useful for us because this implies that in the interior, generically Steklov eigenfunction have isolated critical points, but just for completeness, we have proved 5 because it was for 3 once you do 4. So, and this just is a bypass product that completes, let's say, the statement on generic properties of Steklov eigenfunction. So also in the interior, we have these generic properties. But now, thanks to this, we can apply theorem 1 to Steklov eigenfunction, and essentially what I just state here is the same conclusion of theorem 1, where now U is a Steklov eigenfunction, and this identity holds generically, say, for a dense subset of matrix on a given manifold. Just the difference is that on the right-hand side, the sum of the indexes of phi on the boundary, of the gradient of phi boundary, is taken only where the eigenfunction U is positive on the boundary. In particular, if you want to rephrase this identity in a more, say, simple way, if I call by calligraphic P the set of points on the boundary where the Steklov eigenfunction, or Dirichlet as you wish, is positive, then the sum of the indexes of the critical points of U is equal to the Euler characteristic of M minus the Euler characteristic of P, of the subset of the boundary where the function is positive, where the eigenfunction is positive. So we have this formula relating the counting of the indexes of critical points with some topology of the manifold and also of the, say, boundary nodal domains. Now I will list some corollaries, and especially in a while, which is maybe the most interesting thing, consider specifically surfaces. Well, of course, under the hypothesis of theorem 2, we know that generically these eigenfunctions are Morse in the interior and on the boundary. So we can replace the index with -1 to the Morse index, so just immediate. Also, this is an immediate corollary, is trivial. Again, if P, that is the subset of the boundary where the eigenfunction is positive, is the union of L disjoint connected components, then on the right-hand side, we have the Euler characteristic of M minus the sum of the Euler characteristic of these connected components. Why have I rewritten trivially the identity in this way? Because in dimension 2, each of these connected components where the eigenfunction on the boundary is positive is either an interval, which means that its Euler characteristic is 1, or a simple closed curve, which means that there is a full connected component of the boundary where the eigenfunction does not change sign. In this case, the Euler characteristic is 0. And so we just use this and prove that in case of surfaces, generically, the counting of the index of the gradient of a Steklov eigenfunction is equal to what? To the Euler characteristic of the surface minus this sum. Let me just explain what is this sum. It's a sum of integers. How is obtained? You take all the connected components of the boundary, only those where the eigenfunctions changes sign. So the one where it doesn't change sign do not matter in this count. And on this, you count how many nodal domains there are where the eigenfunction is positive. And this is Lj. And you sum all these numbers. So this is the final formula. And since, again, we are in the case of a surface, and since, again, interior critical points are saddles, we have that the number of critical points is just equal to the number of these sign changings. I will call them like that, sign changes of the eigenfunction on the boundary, minus the Euler characteristic of M. So this is a very precise count for critical points of a Steklov eigenfunction on a surface, which holds generically. Okay, so this is the corollary for surfaces. Okay, I will do now some examples, and I will start with just a simple remark. I already said that in the case of surfaces, we see that the number of interior critical points is determined only by the topology of the surface and only by the components of the boundary where the eigenfunctions change sign. The one where the eigenfunction does not change sign that do not enter in this sum. They do not matter. Let us verify this formula just for fun in some explicit situation. Now I will say something really trivial, but just some, explicit computation that you do just to verify if your formula is reasonable. And let's start with very explicit examples. The annulus, the planar annulus. We take a planar annulus in R2. We take the second eigenfunction. You can take any other eigenfunction. We know them explicitly. And this second eigenfunction changes sign exactly once in the inner boundary circle and once in the outer boundary circle. Well, I'm using an abuse of notation. Changing sign once for me here means that it has only one component where it's positive and one where it is negative. I will call this a one sign change. So please forgive me for that. And the Euler characteristic of the annulus is 0. So our count should give 1 plus 1 minus 0 equal to 2. And in fact, any eigenfunction on the annulus has only 2 critical points, which are saddles. Here is the graphic. Just an example to see if things work, but also to see other things. I will tell in a few moments. Another explicit example that can be done is the cylinder, the flat cylinder, S1 times minus LL. I call L star, that is the usual magic number in these problems, the unique positive root of the equation L, hyperbolic tangent of L, is equal to 1. This is, special number. If L, the height of your cylinder, half height of the cylinder, is less than L star, a second eigenfunction changes sign exactly 1, again, this abuse of notation, on each connected component on the boundary. And so the situation is exactly the same as those of the annulus. And we have two critical points. On the other hand, if L is greater than this L star, the second eigenvalue is simple. And the second eigenfunction is just the vertical coordinate. This is really a trivial thing to look at. So the second eigenfunction doesn't change the sign on each of the two components of the boundary. And so our formula gives that the number of critical points is 0, which is trivially true, of course. This is also for any disk in 2, for example, we have the second eigenfunction is a coordinate function. It changes sign only once on the boundary. The Euler characteristic is 1, so the count gives 0. We have no critical points, which again is really trivial since this is a coordinate function. However, we recall that for a simply connected planar domain or even a surface, the second eigenfunction, the second Steklov eigenfunction, has no critical points, and this is a result of Payne and Philippon of 1991. So this is well known that for simply connected domains of the plane, a second Steklov eigenfunction has no critical points. Yes, the case L equal L star. Give me a few moments. I will speak in a while. Okay, so a few remarks. In the case of the cylinder where L is greater than L star, so when we have that the eigenfunction is constant on each of the two boundary components, this eigenfunction is not Morse on the boundaries. The restriction on the boundary is not a Morse function, it's constant. However, it seems that the counting formula is still valid. But maybe it's just we were lucky. Okay. What did I do? Okay. And recall that our counting formulas hold generically. So morally, what does it mean generically? That if I ask you, think to a random domain and tell it to me, then it is almost sure that for that domain, these formulas will hold, let's say, morally, like that. But if I really ask to you this question, the first domain that you tell to me is the disk or the sphere, the first one that comes into mind. But then usually for this, as always, for these domains, this generic stuff does not hold because of the symmetries, because of many reasons. And usually, in fact, many generic properties fails for disks or balls. In fact, Steklov eigenfunction could not be Morse. Here you see I've plotted for the disk the graph of some Steklov eigenfunction. You see that the second and the third one that I've plotted are not Morse function. 0 is a degenerate critical points. They could have singular zeros. All the three here have singular 0. They have a point where the function is 0 and the gradient is 0. So clearly for the disk, as always, generic stuff does not hold. But also in this, say, worst case of the disk, the second eigenfunction as second eigenfunction is Morse, and it has no singular zeros, also in this worst case. So the natural question, looking at this and also the sample of the cylinder, is that some of the previous result holds for a second eigenfunction in dimension 2, not just generically, so they hold always. In particular, if the formula for the counting of the critical points of the second eigenvalues, the one with the Euler characteristic and the number of sign changes, still holds, but not generically for any metric. Okay. So this is what we have tried to figure out then, to establish something that is not generic. And let me, just for the purpose of this talk, I will state this in a simple situation. It is the second eigenfunction at genus 0 surfaces. Then this is true also in other situation. So I consider a smooth compact surface of genus 0 and smooth boundary, which means a planar domain or a domain of the sphere with boundary. Then we have always these three facts. The second eigenfunction is always Morse. So second eigenfunction on a genus 0 surface is always a Morse function. So this is not generic stuff. The second one is easier, maybe it's nothing special. It has no interior singular zeros. Actually, we don't really need that for our purposes anyway. And the third one is that actually it came out from our proof that if you have on the boundary of genus zero surface a zero of the second eigenfunction, then either it is non-singular, which means the gradient does not vanish, or if the gradient vanishes, this zero is not degenerate, means that the Hessian is positive or negative definite. In particular, in the simply connected case, singular zeros cannot occur. So if you have a zero, the gradient cannot be zero on the boundary. And this comes out from the proof of these three properties. But let me again do some remarks on this theorem that we proved. This property holds not generically. The other property that we needed, that the second eigenfunction is Morse on the boundary, this cannot hold in general. So as the example of the cylinder shows. So this we cannot have in general for the surface. From our proof of point 3, we are left with the question, okay, from the proof it seems that you can either have no singular zeros on the boundary, or if you have a singular zero, it must be non-degenerate. The question is, can happen that you have a singular zero even if it is non-degenerate, or it is a matter of our proof that we have this other situation? Actually, this is in fact possible. You take, in fact, the flat cylinder S1 times minus L star, so with exactly this L star as height. And so here the second eigenvalue is triple, and you can manage to find the second eigenfunction, which behaves exactly like that. It has two critical points which are on the boundary. So these are two zeros which are critical points and are on the boundary. These are singular zeros, and these are non-degenerate. You see that the nodal lines, which are in red in this picture, meet at the boundary with an angle of pi over 2, as expected, and form an angle of pi over 4 with the boundary. So the theorem is sharp. Only these two situations can happen for a second eigenfunction on a surface. So we cannot have higher order of degeneracy of a boundary zero. But this can happen. But this is not really bad. At the end, this situation is not really bad. We can control it. And the proof of this result uses the fact that around singular zeros of harmonic function, the behavior of the zero-level sets can be described explicitly. Then we use some topological consideration and also an argument saying the spirit of Payne and Philippin of 1991. Let's say. So for this theorem, I don't enter in the details. The problem is that, again, we cannot apply theorem 1 because we have proved that it enjoys properties not generically, but not all the properties that we want, because it's not Morse, it's not always Morse on the boundary. So we cannot apply theorem 1. And so we need to apply a following variant, the following variant of Poincaré-Off. So I try to describe it, but roughly. If we have on a surface with boundary a smooth vector field with isolated zero and which has no zeros on the boundary, and for which the vector field is not always outward pointing, so we cannot apply Poincaré-Off, then under suitable assumption, we know that the sum of the indexes is equal to the Euler characteristic of M minus the Euler characteristic of P, where P is now the set of points on the boundary where the vector field is outward pointing. But you need other condition to get that. I don't read them anyway, but you can check that for Steklov eigenfunctions, they are in the surface, they are satisfied. And the proof of this consists in perturbing the field in the places where it is inward pointing in order to obtain now a field that is always outward pointing. You do it in a suitable way, such that you create a control the precise number of new interior critical points, and then you count them, and then you get the formula. But if you wish, we realize that this could be also deduced by a result of Morse of 1929. Anyway, we would like now to apply this. The point is that, again, in the hypothesis, we don't want zeros of the field on the boundary. And as we have seen, the second eigenfunction can have singular zeros at the boundary. But as I told you, they are non-degenerate, so they are really well behaved there. We know exactly how they behave. So again, we can perturb the gradient vector field in a boundary of the singular boundary 0 without producing new interior critical points. And then we apply the previous theorem. And then let me just get to the conclusion. We get the theorem that we wanted, that the number of interior critical points of a second eigenfunction on a surface of genus 0 is always equal to the number of sign changes minus the Euler characteristic of the surface. So this is not a generic result. It also for all these surfaces of genus 0, and also in other situation, but just to simplify the presentation, I just state it for genus 0 surfaces. Okay, I just want to finish the last 10 minutes. Yes, that's 3 minutes. It will not take much, with some final comments. So what we did so far we established some formulas which related the interior critical points of Steklov eigenfunctions with the topology of the domain, and that of the boundary nodal domains of the eigenfunction, which are the nodal domains of the Dirichlet-Neumann eigenfunctions. These formulas are valid in any dimension and become more explicit, as we have seen in the case of surfaces. These are generic formulas, but for U2 and genus 0 surfaces, they hold for any metric. So why, among various purposes, why we started to look at these critical points among all other possible purposes? We wanted just to try to recover just a bit of information on the nodal count of the Dirichlet-Neumann eigenfunctions in higher dimensions, so on the number of boundary nodal domains of Steklov or Dirichlet-Neumann eigenfunction. Because I recalled you at the beginning that these quantities, number of critical points, number of nodal domains, multiplicities, are all related. So maybe one can do can walk around and try to attack the problem from the point of view of critical points. Maybe we wanted to try. And this was motivated by an open question that one can find in the Steklov surveys that we all know well. And the question is the following: can a second eigenfunction have an arbitrary number of boundary nodal domains in higher dimensions? You can replace second by kth eigenfunction. More generally, the question is, does a current type theorem hold for the Dirichlet-Neumann eigenfunctions? Means that you can bound the number of boundary nodal domains of the kth eigenfunctions in terms of k and the dimensional constant. Let me rephrase again. Look at this picture. You have a ball and you have this hypersurface, which separates the ball into the interior of the ball into two connected components, but separates the boundary in many components. So the point is there a metric on this ball for which this is exactly the nodal line, the nodal set of a second Steklov eigenfunctions? So these are equivalent ways of stating the same question. So the validity of this kind of bounds is maybe being suggested, maybe because in the case of cylinders, balls, or places, domains, manifolds for which we can do computation seems to be true. Of course, our formulas, finally, we realized that cannot help to attack this problem from the critical points side. So this was not helpful to verify or disprove the conjecture. In fact, the point is that there are no current type bounds for Dirichlet-Neumann eigenfunction. And in fact, but this is another story, we recently proved this theorem. If you take a compact smooth manifold of dimension n greater or equal than 3 with a smooth boundary, and you choose any separating hypersurface, like the yellow one here, any, with boundary which belongs to the boundary of the manifold, then you can find always a smooth Riemannian metric on the manifold, such that sigma is the zero level set of U2, but also of UK. But this is another story. It was not the subject of this talk. Maybe another one, I don't know. And okay, I stop here. And meantime, yes, and I thank you for your attention.
Thank you very much, Luigi, for your very nice talk. So if you have any question or comment, you can unmute yourself or put your question in the chat. So maybe I open the floor
Yeah.
to questions. So for higher dimension, your result is, so there was part of the result that it was non-generic for all metric in dimension 2. So for higher dimension, you cannot say anything.
For higher dimension, no.
Or
Actually, let me say the truth. For higher dimension, I haven't thought about that, but maybe it is more complicated because you don't have a so neat explicit description of say nodal lines of harmonic function of Steklov eigenfunction. It's it's not so neat as in dimension 2, so maybe it's more difficult to establish non-generic formulas of that kind. Yeah.
Any other questions or comment? Yeah, maybe about the last theorem. You said it's not part of this talk, but it's
no, it's
very
not part.
interesting.
But actually,
yeah.
the point is that we wanted to attack, of course. Then we realized that it was hopeless, but from the point of view of critical points, and then finally we realized that. Yes,
So
please.
may I ask about the idea? So how you construct, like if it's easy to say, like very briefly.
Maybe
like...
if you wish, maybe I can explain you after.
Okay. Yeah. Yeah.
Or now, if you wish, but after the so we don't keep all here.
Okay.
You know.
Yeah.